Quantum computing advances simulation of superconductivity. Quantum computing advances simulation of superconductivity. Recent advances in quantum computing offer a promising new avenue for understanding and potentially unlocking room temperature superconductivity. Researchers at Quantinuum, a quantum computing firm, have utilized their new Helios 1 quantum computer to simulate a mathematical model central to the study of superconductivity, marking a significant step towards harnessing the power of quantum computers for materials science. Understanding superconductivity and the Fermi-Hubbard model superconductors possess the remarkable ability to conduct electricity with perfect efficiency. No energy is lost. However, current superconductors only function at extremely low temperatures, hindering their widespread application. For decades, physicists have sought to identify ways to modify the structure of these materials to enable superconductivity at room temperature. A key framework for this pursuit is the Fermi-Hubbard model, a mathematical description considered one of the most vital in condensed matter physics. Classical versus quantum simulations. Conventional computers can effectively simulate the Fermi-Hubbard model, but they face limitations when dealing with very large sample sizes or systems where the material's properties change over time. Quantum computers offer the potential to surpass these limitations. Quantinuum's recent work represents the largest simulation of the Fermi-Hubbard model conducted on a quantum computer to date. The Helios 1 simulation. The research team employed the Helios 1 quantum computer, which consists of 98 qubits constructed from barium ions and controlled using lasers and electromagnetic fields. The process involved carefully manipulating the qubits through a sequence of quantum states, culminating in the measurement of their properties to produce an output. The simulation focused on 36 fermions, the type of particle found in superconductors and described by the Fermi-Hubbard model. Simulating electron pairing, a key step, a critical process in superconductivity, is the pairing of these fermions. Experiments have shown that this pairing can be initiated by laser pulses. The Quantinuum team recreated this scenario in their simulation, exposing the qubits to a laser pulse and subsequently measuring the resulting states. These measurements indicated evidence of the simulated particles pairing, mirroring a crucial element of superconductivity. Although the simulation did not perfectly replicate experimental results, it successfully captured a dynamic process challenging to reproduce with conventional computer methods when applied to more than a few particles. A growing competitive edge, while researchers caution that this experiment isn't a definitive proof of Helios 1's superiority over all traditional computing approaches. Their investigations into classical simulation methods led them to believe that a quantum computer could effectively compete. For the methods they explored, achieving consistent and comparable results with classical computing became a significant challenge. The estimates for classical computation times were so long it was difficult to determine when they would match the Helios 1's performance. Hardware and future potential. The team credits their success to Helios 1's robust hardware. According to David Hayes, also at Quantinuum, the qubits are exceptionally reliable and excel at industry-standard benchmarking tasks. Moreover, Helios 1 demonstrated the ability to sustain experiments with error-proof qubits, and crucially, connected 94 of these qubits through quantum entanglement, a record among all quantum computers. Utilizing such qubits in future simulations promises to further enhance accuracy. Ongoing validation and broader implications. Eduardo Ibarra Padilla at Harvey Mudd College acknowledges the promising nature of the results, but emphasizes the need for careful benchmarking against advanced classical computer simulations. The long-standing importance of the Fermi-Hubbard model, which has intrigued physicists since the 1960s, makes this new tool for its study particularly exciting. While predicting precisely when quantum approaches like those used with Helios 1 will genuinely rival the best conventional computers remains uncertain, numerous refinements are still needed. Steve White at the University of California, Irvine points to the challenge of ensuring quantum simulations begin with precisely the right set of qubit properties. However, he envisions quantum simulations becoming a valuable complement to classical methods, particularly for modeling dynamic or changing behavior in materials. They are on the way to becoming useful simulating tools in condensed matter physics, he concludes. But they're still in the early stages. There are computational barriers still to come. The research offers a glimpse into the potential of quantum computing to unlock the secrets of superconductivity, paving the way for revolutionary advances in energy efficiency and technological innovation. Reference: Archive DOI 10.4855 Archive 2 5110 2125.